In this video, we'll discuss estimation, which has many applications to surveys and polling. So far in this class, we've dealt mostly with problems where the parameters of the distribution were known, and the goal is to calculate probabilities. So here's an example of the kinds of problems we've looked at. So there are 160,000 registered voters in SLO County, and let's suppose that we know that 53.4% of all registered voters plan to vote for Gavin Newsom for governor. Now, a simple random sample of 200 registered voters is taken. That just means we choose 200 people at random without replacement because we don't want to poll the same person twice. And a question you might be used to answering is, given this information, what is the probability that more than 55% of the voters in the sample of 200, support Newsom for governor? So you could solve this by noting that the number of people in the sample who support Newsom, X, has a hypergeometric distribution because we're sampling without replacement, and we're polling 200 people from a population with 85,440 Newsom supporters. That's just 53.4% of 160,000, and 74,560 non-Newsom supporters. And now we want to know the probability that more than 55% of the voters in the sample support Newsom. In other words, the probability that X over 200, that's the percentage of people in the sample who support Newsom, is greater than 0.55. Now, this question is not very realistic. If we already knew that 53.4% of all registered voters support Newsom, why would we bother taking a simple random sample in the first place? The point of taking the simple random sample is because you don't know how many registered voters plan to vote for Newsom, and you want to be able to estimate it. So here's a more realistic example. There are 160,000 registered voters in the county, and an unknown percentage of these registered voters plan to vote for Newsom. Let's call that unknown percentage P. We take a simple random sample of 200 voters, and we find that 55% of the voters in our sample support Newsom. Based on this information, what is our estimate? What is our best guess for P? Well, now the number of people in the sample who support Newsom, it still has a hypergeometric distribution, still with n equal to 200, because we're still taking a simple random sample of 200 people, but now n1 and n0 are unknown because they depend on P, the percentage of all voters who support Newsom. Now, we've happened to observe that X divided by 200 is 0.55. What does that allow us to say about P? Well, our best guess for P is of course just 0.55. So we call 55% our estimate of P, and X divided by 200 is the estimator of P. So an estimator is just a general rule for coming up with an estimate given data X. So if X had instead been 100 out of 200, then our estimate would have been 0.5. So an estimate is a specific number, while an estimator is a general rule for coming up with an estimate. So is 0.55 a good estimate of P? To answer that question, we look at whether X over 200 is a good estimator. So let's first calculate the expected value of our estimator X over 200. And keep in mind that X has this hypergeometric distribution. So to calculate the expected value of X over 200, we note that X over 200 is just 1 over 200 times X, a constant times X. So we can bring that constant outside the expected value. And now the expected value of a hypergeometric is just little n times n1 over big N. So little n is 200, n1 is 160,000 P, and n, the total number of people in the population, is 160,000. So the 200s cancel, the 160,000s cancel, and we're just left with P. So on average, in other words, an expected value, our estimator x over 200 equals the thing it's estimating, which is p. This is a good property for an estimator to have. If the expected value of an estimator is equal to the thing being estimated, then the estimator is said to be unbiased. Now, we'd also like to know something about how variable our estimates can be. So to measure this, we'll calculate the variance of our estimator x over 200. So this is the variance of 1 over 200 times x. We can bring out the constant, but we have to remember to square it when we bring it out. Now this is just the variance of a hypergeometric random variable. So we just plug in numbers into the formula. The formula for the variance of a hypergeometric is n times n1 over n times n0 over n times this finite population correction factor. So we have 200 times p times 1 minus p times this finite population correction factor. So now the 200 cancels with one factor of 200 down here, and we have p times 1 minus p, and this finite population correction factor is very, very close to 1. You can try calculating it if you don't believe me, but that's because our sample size is very small compared with our population size. So the variance of our estimator is about p times 1 minus p over 200. So the standard deviation is the square root of that, the square root of p times 1 minus p over 200. So this tells us how much we're likely to be off by. Of course, one problem with this formula is that we don't know what p is, but we can plug in our best guess for p, which right now, based on our sample of size 200, is 55%. So if we plug that in, we get that the standard deviation is about 0.035. So to summarize, our best guess for p, based on our sample of size 200, is 55%, give or take 3.5%. That's how we interpret this standard deviation, how far we are likely to be off by. And this 3.5% is often called the margin of error for the poll.